In this lesson, we are going to talk about the properties of exponential relationships and what type of problems can be modeled by exponential relationships. We have already seen situations that you can use linear or quadratic relationships, but there are many other cases that neither of these models can really be applied to the situation. For instance, for the growth of a bacteria or the compound interest problems or the rate of decay or growth of the radioactive materials, these are the situations that neither linear or quadratic relation can be applied. In general, the graph of an exponential relation is a curve that on one side it is almost horizontal to x-axis, as you can see here or here, and on the other side it is increasing rapidly. Here you can see the increase, and here you can see the decrease. Now you may say, how do I know that it's increasing or decreasing? It's very simple. You always go from left to right on the x-axis. If I go from left to right on the x-axis, I look at the y values. If the y values are going up, then it means it's increasing. Here you can see that the y values are going up. So this is a rapid increase. In this case, going from left to right again, you can see the y values on this side are going down. So this means it's decreasing. This situation is called decay. This situation is called growth. Now, in an exponential relation, for equal increase in x or y, doesn't matter what, the other variable is going to have the same ratio. This is very important because we are going to use the ratios to find out if a table of values represents an exponential equation. The first example is asking if the following table of value represent an exponential relation. In general, when you have a table of values, you try to see if it's linear, exponential, or quadratic, or none, meaning neither of these relations. To see if it's a linear, we always go to the first differences. So let's do this one for this table of values. To find the first differences, I'm going to subtract 2 from 4, so I get 2 here. Then I subtract 4 from 8, I get 4. I subtract 8 from 16, I get 8. I subtract 16 from 32, I get 16. I subtract 32 from 64, I get 32. You can see that the first differences are not the same, so this is not a linear. To find if it's quadratic, I find the second differences. I do the same thing. I'm going to subtract 2 from 4, I get 2. Then 4 from 8, I get 4. Then 8 from 16, I get 8. Then 16 from 32, I get 16. You can also see that the second differences are not the same, so you say that this is not a quadratic. The last thing we are going to check is the ratios. Remember, I said in an exponential relation, the ratios of the y or the x's are the same. Let's find the ratios in the y. I'm going to divide 4 by 2. I get 2. Divide 8 by 4. I get 2. divide 16 by 8, I get 2. Divide 32 by 16, I get 2. And 64 divided by 32, I get 2. You can see all the ratios are the same, so we can say that this is an exponential relation. The next question says, which of the following graph represents an exponential relation? Explain. Part A, you can see that this one is a linear relation because it resembles a line. Part B, we can see that as we go from left to right, the value of y is increasing. This represents an exponential growth. This one, part C, represents a quadratic because from left to right you can see that the y value increases up to this point and then starts decreasing here. This one, as I go from left to right, you can see that the y values are increasing, then they start to become something like a horizontal line. This also represents an exponential relation. So B and D, they represent exponential relation. The next question says you have a large pendulum which is set in motion, and with each complete swing, the pendulum's maximum distance from its rest position decreases. This represents a situation. This represents a situation like this. This is your string, this is your bob. Now the pendulum is moved here and starts going left and right. This is the rest position here. The distance from the rest position is this distance. You can see initially is the maximum, then as the pendulum moves left and right, the distance decreases until the distance becomes 0, meaning that the pendulum stops right in the middle. Now, for every 5 swings, we have measured the distance from the rest position. At the beginning, which is here, is 23.5. After 5 swings is 19.9, and so forth, until the 30th swing. The first part of the question says, make a scatter plot of data, describe the graph. Now to plot the table of values, the first thing I'm going to do to accommodate all the y values, I'm going to multiply these numbers by 3. So this becomes 6, this becomes 12, this becomes 18, this becomes 24, and this becomes 30. To accommodate x values, I'm going to renumber here. So I'm going to make this one to be 5, this one to be 10, this one to be 15, this one to be 20, this one to be 25, and here to be 30. Now, when x is 0, y is 23.5, so it's going to be a point somewhere around here. When y is 5, x is 5, y is 19.9, so it's going to be somewhere around here. When x is 10, y is 17. When x is 10, y is 17. So it's going to be somewhere around here. When x is 15, y is 14.6. So it's going to be somewhere around here. When x is 20, y is 10.4, 20, y is 10.4, which is going to be somewhere around here. When x is 25, y is 8.7, which is somewhere around here. And when x is 30, y is 7.6, which is going to be somewhere around here. Now, this graph can be modeled by an exponential relation because as we go from left to right, the y values are decreasing. The initial value of y is 23.5, and as the number of swings increases, the graph becomes something like an horizontal one, and it continues until the distance becomes 0. Now, the other way that we can see if it's really an exponential one is we can find the ratio and we can see if the ratios are almost constant. To find the ratios, as you can see here, I'm using Excel. This column represents the number of swings. This one represents the maximum height, the maximum distance. To find the ratio, I'm going to divide 19.9 by 23.5, and the answer is 0.847. Then 17 divided by 19.9 gives you 0.854, and so forth. And you can see these numbers, although they are not exactly equal, but they are almost the same values. This tells us that if we try to fit an exponential relation to this set of data, we get a good representation. The next question says, is this relationship an example of exponential growth or exponential decay? If we look at the graph, this is the table of values that we had, and this is the graph. When we plot it on Desmos, you can see that the graph represents an exponential relation going from left to right. The y values are decreasing, so this is an exponential decay.